from these examples, you can probably see that there are some things that you need to be careful about when you go ahead and do integration by parts. So integration by parts can only be used if the integrand satisfies the following conditions. First of all, the integrand can be written as the product of two factors u and dv. Second, it's possible to integrate dv to get v and to differentiate u to get du. If that's possible, then 3, that new integral that we get, the antiderivative of v du, had better be something that we can do. If it's not, this isn't a very effective strategy, and maybe you need to go back and pick a new u and dv. In most of these problems, there's going to be only 1 or 2 ways to pick the u and the dv, so if one of them doesn't work, switch them around and see what happens. So here I have a new antiderivative, the antiderivative of x squared e to the x dx. This is a lot like the first one we did, except the first one was x e to the x. This one's x squared e to the x. And what you're going to see is it has a little bit more work to it. We're going to go ahead and apply our integration by parts. And remember, when we do that, we have to think of this as the antiderivative of u dv and match up the pieces from our integrand. What we're going to do is we're going to say u is x squared and dv is e to the x dx. We could choose these exactly backwards, but if we did, the new integral we get back would be a lot more complicated than the one we started with, which tells me that's probably not a good direction to go in. Now that I have that u is equal to x squared, the derivative of u with respect to x is 2x, and when I multiply both sides by dx, I get that du is equal to 2x dx. Our dv is e to the x dx, so dividing both sides by dx, I get that dv over dx is e to the x, and the antiderivative of that is v equals e to the x. This allows me now to use my integration by parts and write down the pieces. So remember, we have to have uv, which will be x squared e to the x, and then we'll have v du, which will be e to the x times 2x dx. So when I write that down, I get x squared e to the x for the uv, and then when I go ahead and do the antiderivative of v du, I get e to the x times 2x dx. Now looking at this new antiderivative, the original had x squared times e to the x. This one has 2x times e to the x. It's a little bit easier because the power dropped down, and that's because when we took the derivative of x squared, we got 2x. But this is still a fairly difficult antiderivative for us to do, but what we can do with this is we can do integration by parts a second time. The second time I do it, I'm going to let u equals 2x. I'm going to let the dv again be e to the x dx. Now when I take the derivative of u, I get 2, so that means du is 2 times dx. When I do my antiderivative of e to the x, I get that v is equal to e to the x. And now in my integration by parts from this integral, I get something a lot easier. So I get uv, which in this case will be 2x times e to the x, minus v du, but in v du now it's e to the x times 2, and we can just bring that constant right out in front, which means this is just the antiderivative of e to the x, which is e to the x. So we end up getting inside the parentheses, we get the antiderivative of e to the x times 2 dx is just e to the x times 2. We'll go ahead and distribute our negative, add on our constant. So what we end up getting is x squared e to the x. That came from the uv when we did integration by parts the first time. And now we get two more terms, minus 2x e to the x. Well, that came from the uv when we did integration by parts the second time, plus 2e to the x plus c. So we get more terms here because we actually did integration by parts twice. But notice each time we did integration by parts, that piece of the product that had x squared in it originally dropped down to 2x and then down to 2, which eventually meant that we had an easy antiderivative to do.